Now, moving on to the main event of this morning's general session, our 3 keynote speaker presentations. The keynote speakers of the general sessions of WorldComp have always been delivered by individuals whose work has had a lasting and significant impact to our field. In recent years, the keynote speakers of the Congress included, and this is just a partial list, Professor A.J. Siegel, at the time he was at Purdue, but now at Colorado State University. Dr. John Gustafson, now at Massively Parallel Technologies. He's the CEO. He was the inventor of the Gustafson's Law. Professor John Koza from Stanford University, inventor of genetic programming. Professor Richard Michalski, known as the father of machine learning from George Mason University. Professor Barry Vercoy from MIT, the founding member of the MIT Media Lab. Professor John Holland from University of Michigan, father of genetic algorithms. Professor David A. Patterson from University of California at Berkeley. He's been presenting talks multiple times in this Congress. Ms. Anusha Ansari, CEO of Purdue Systems and also the first female private space explorer and the first astronaut of Iranian descent. Professor Ian Foster, known as father of grid computing of University of Chicago and also Argonne National Lab. Dr. K. Eric Drexler, known as father of nanotechnology. He's Chief Technology Advisor to NanoRex. Dr. Jose Munoz, formerly Deputy Director of National Science Foundation, plus Director of ASCII Initiatives of NSF and DOE. Professor Lotfi Zadeh, known as father of fuzzy logic, University of California, Berkeley. Dr. Firuz Naderi, Associate Director of Project Formulation and Strategy from Jet Propulsion Lab, and also Caltech, NASA, and head of NASA Mars Exploration System. He's the guy who made the Mars rovers a reality. He was the director of that initiative. Professor David Parnas from McMaster University. He developed the concept of information hiding, which is an important element of all object-oriented programming. Professor Eugene Spafford from Purdue University and Executive Director of Sirius, a security center at Purdue University. Professor Victor Raskin, Distinguished Professor at Purdue University and Associate Director of Sirius, together with his former PhD advisee at the Hebrew University of Jerusalem. Dr. Raskin developed a groundbreaking ontological semantic approach to NLP that for the first time aspires to near-human comprehensive semantic capabilities for NLP systems. Well, our first keynote speaker, Professor Amit Sheth. As chair of the steering committee of this Congress, it gives me a great pleasure and honor to introduce our first keynote speaker, Professor Amit Sheth. Professor Sheth is an educator, researcher, entrepreneur, visionary, and leader. He's the LexisNexis eminent scholar and founder and executive director of the Ohio Center of Excellence in Knowledge-Enabled Computing. And the acronym that he uses for that center is NOESIS at Wright State University. NOESIS conducts research in social, sensor, semantic data, and Web 3.0 with real-world applications and multidisciplinary solutions for translational research, healthcare and life sciences, cognitive science, material sciences, and others. NOESIS activities have resulted in Wright State University being recognized as the top organization in the world on World Wide Web in research impact. Professor Sheth is one of the top authors in computer science, World Wide Web, and databases. His H-index, if you know about H-index, is kind of a measure of how the quality of the work that is published and the citations associated with it. His H-index is 86. Mine is 18. I'm so proud of it. Okay? His research has led to several commercial products, many real-world applications, and 2 earlier companies with 2 more in earlier stages of development. One of these was Tally, then changed the name to Verquid Semagics, which was likely the first company founded in 1999 that developed semantic web-enabled search and analysis and semantic application development platforms. He is one of the highest cited authors in the world in computer science. He leads one of the largest academic research groups in the area of semantic web. Every year, this Congress presents 2 outstanding achievement awards to a very few selected researchers and scientists in recognition and appreciation of their dedicated and outstanding contributions to their respective fields of research. As the chair of the steering committee, it gives me a great pleasure and honor to present one of this year's awards to Professor Amit Sheth in recognition of his leadership, outstanding research contributions, and pioneering work in the field of semantic web. Professor Sheth, please come to the podium. Professor Sheth's keynote address today is entitled Smart Data for You and Me, Personalized and Actionable Physical Cyber Social Big Data. Our invitation, and please accept this plaque.
Oh.
Well, you have to wait. Thank you.
Thank you.
Okay. It's all yours.
Ready? All right. Thank you very much for this opportunity to speak at this significant event, this Congress. Thank you, Hamid, for the invitation and the steering committee. I have a title, perhaps some of the names or rather terms might not be totally clear to everyone. I hope to introduce them to you and discuss their significance with you. So we'll talk about smart data for you and me, for individual and for community, and this emergence of physical cyber social computing, applications in which data from the physical world, from the cyber world and social world come together to enable new class of very exciting, very important applications. Very briefly about the big data, and I don't want to dwell here much into that. There will be many other talks, many other discussions on that later on, but the growth is amazing. In 2008, we lost the ability to store all the data that we create, and every year we kind of create more data than we created beforehand. And that, somehow the slide didn't come out too well, but we have such a growth of data that only 0.5% of all the data gets processed and gets analyzed, right? So much of the data simply is not stored, much of the data cannot be analyzed. So besides the volume issue on which many people have paid some attention, the other issue, the one that actually gives more complexity, more difficulty, is the variety issue. And that includes you have data of all kinds, semi-structured, unstructured, and you have data of all modality, audio, video, and images. And the fact that the data continuously changes. You talk about an event, and in an event something happens, let's say a Hurricane Sandy. Before the storm comes on shore, there are some topics of discussion, and then during the landing, there are other topics of discussion, like light goes out. And after the storm has moved out, there are other topics of conversation, such as lack of some resources. So data changes fast, and being able, that's called velocity aspects of it. So the volume, variety, velocity, veracity, these are some of the V's that people talk about in the context of big data. But beyond that, and the one that I will probably talk about more today, is that for the first time in the human history, we have one tool that majority of the humanity has, right? And what tool is that? That's the mobile phone, right? No time in the past we had a single tool that majority of the humanity had, right? So this is fun. And because of that, so there are, 2 billion of the 5+ billion people, I think probably 6+ billion people now, that have data connections, right? There are smartphones. In a couple of more years, majority of the people who have phones will have smartphones. In addition to that, there are a lot more sensors not going on, and this term called Internet of Things is now becoming very popular. At the two of the largest exhibitions and conferences, the SXSW and the CES, the two was the most important keywords or hashtags were IoT and digital health. And in my talk, we'll talk about challenges in actually in dealing with these two issues. So there are well over 10 billion devices that communicate over the internet. These are Internet of Things, and that the numbers are growing and will grow very, very fast. So now, and the different terms beyond IoT, people have also called it, Cisco has called it Internet of Everything. That everything includes both the devices and the humans that use these devices to communicate. So mobile phone, you have human in the loop computing, human in the loop sensing, and humans, when they see something, they share with people through tweet or some other method. With that then, there is emergence of what I call this physical, cyber and social worlds coming together. So what has not changed? We are still working with rather simplified presentation of information. Majority of the computing that we do today, major of the activity that our algorithms, major of the data that our algorithms process are usually data of singular type. There's a lot of work on text processing, there's a lot of work on image processing, a lot of work on video processing. But the human being, we are multisensory, right? At the same time, you are consuming the video of watching me and watching this thing. You are reading, and you are processing natural language, and you know, so you have multimodal information always coming at you, and you take about a traffic event, you will have a tweet about it, you will have road sensors about it, and many other things coming together. So we need to be able to have a computational paradigm that deals with more diverse forms of data, not only different types of data in a representational sense, but the different types of data in the sense of the data capturing the physical world, capturing the social interactions, capturing information of the web. So the nutshell of this talk is that current emphasis on big data is on enterprise, serving the enterprise and corporate needs. There is significant opportunity for applications that deal with individual and community needs, right? So with the corporations, we can benefit so many people. But if we develop applications that can serve your and my needs, we will be affecting a lot more people. And interestingly, I will show you, if you are not already aware, that in fact all of us already have a big data problem of sorts. Should we recognize all the data that is being relevant to things we do, our existence, our health? So the applications in the domain, particularly health, fitness, well-being, disaster coordination, personalized smart energy, these are some of these where we can exploit diverse data. And as a way of thinking, as a way of new paradigm, I will talk about the smart data, personalized, contextually relevant, actionable information as a better computational paradigm. So think about data, and from that data, you get information. That is good, but that is not sufficient. In fact, what you need is information that is actionable, that is relevant to you. So your actionable information could be that an apple a day does good to you, is good for you, right? So it's not important that there is a data about how many, that something is an apple. What is important is how is it relevant to your decision making? How is it important to your, insight that you need to have? Take an example of now the challenge that we face. Typical blood test has 30 biomarkers. How, and the doctors are supposed to interpret this data into an information and then decide whether there should be something, some health related decision that needs to be made. What would happen when the doctor would have 300,000 data points, right? So this is happening. The amount of information that is being created is so massive. But the computational capability, the cognitive capability of a human brain is not going up that fast. So the interesting thing and the challenge that we have is to convert all this massive amount of data and bring it to the level of abstraction at which it makes sense to human decision making. Right? That is the challenge we have. So there is massive amount of, I've been reading this book, the title is about top brain and the bottom brain. And there is a lot of work in cognitive science, in other disciplines, but in particular in this case cognitive science. Many of you know that in dealing with big data, we have done great progress in machine learning, right? Being able to have some training data, have the algorithms find some patterns and then give you new data. They can do the classification, they can find those patterns and such. That's fine. So you do pattern, understanding or recognition, mining, and so on and so forth. At the same time, we also need to engage top-down processing. So the idea of the top brain is that it can plan. It can, based on planning, it can say what other data to seek out, what other pattern to seek out. So rather than just rely on the bottom-up processing, which is where techniques like machine learning are used, we need to combine with that the top-down processing. And together, things we can develop much smarter, much better algorithms. Right? So if you think about, and in the computational terms, we talk about infusion of models and background knowledge, knowledge and reasoning, things of that nature. So think about the sensor in your refrigerator, which has count of number of apples in your fridge. This is data, but that is not very useful. And the fact that you have few apples not enough apples in your refrigerator would be information, but that itself is not sufficient. What will be important is that when you are at a grocery store, at that point you being reminded that you are low on apple, and that basically that leads to the action of your buying more apples for you. That is important. That is that's where you want to go to. And the other interesting thing here is that in all this context, you cannot simply rely on the machine to do all the things for you. What if you are tired of having apple all these past months? Today you want to pick up another healthy fruit instead of apple, right? So the human involvement in that process is also very critical, right? So there are a number of things that I talk about here, about data to information, to actionable information, and the human role, which makes for very exciting computation. So we have contextual information that makes sense to humans, not just machines. Makes sense to machines, that's also good. That leads to better, timely actions. That is what I call smart data, right? Now, it so happened that Hamid mentioned that I had started a company in 1999, a semantic web company, and it got acquired and acquired and acquired. It still exists, by the way. The technologies we developed still exist, and is deployed at majority of the biggest banks in the world for financial applications. But I wrote something there in 2004, 2005. Recently I was using this term smart data, and then I Googled and I found my own old article and white paper and industry talks because there was a company. So use of ontologies and data repositories to gain relevant insight, and you can see the smart search and things of that nature. You can see the here you can see the ontologies or knowledge representation, all the annotations of the data with regards to the term in the ontology, and then using all that for smart search. This is very similar to basically knowledge graph. These days you hear about Google Knowledge Graph, and using that knowledge graph you basically annotate or tag all those terms, and then Google has this result about when you do search, you may get result about somebody. We used to call rich media objects in those days in our company. They call it something else now. and much of this detail you can find in a patent that was already awarded in 2001. But anyway, that's where we use the term smart data. Today, I will kind of define that as smart data makes sense out of big data. It converts all these challenges in volume, variety, velocity, veracity into value. And value is that of making this data, converting this data into actionable information and help humans make better decisions. I have another definition, which is that smart data is of human, by human, for human. Right? So here the idea here is that you want to extract value out of all this data and use it, basically throughout the data creation, processing, and consumption phase to again improve the human experience. So another term that I use is computing for human experience. That the whole idea about computing is to serve human and to improve our experience. I don't like the general way in which we have computers do the job for us. Most of the time, we have to convert our rich real-world environment into something very narrow, aspects of what you can convey to the computers using our rather limited programming languages and rather limited data structures and data types, and get simplified answers to the simplified information we feed, and then interpret that in the real world. That is generally what we do. But things are changing now. Things with ambient intelligence and many other things that are happening. The computing is becoming more aware of human activities. Rather than human going to computer and telling about everything that he or she is interested in, let the computer and environment and the technology be more aware of you and what you are interested in. A beautiful piece that Mark Weisner wrote in 1991, Computing in the 21st Century. He said that technology should disappear in the background, right? So that general theme is throughout what I try to do. Let's talk about of the human. So you have data of the human whereby today you have all this quantified self, the Fitbit and smartwatches and all that thing. That is data about you. You have sensors around you, on you, and in the body. There are ingestible sensors that will actually take photographs and then give you inside a video when the sensor comes out. Then there is data that is about your interaction online. Again, that is data about you, right? That is what you do. You say, oh, I am at Las Vegas, prepared, all ready to give my talk. There can be near-field communications, and our mobile phone can know who are among the people that we already knew that we met today, and so on and so forth. Then there is data by human. We will engage in creating a lot of data. So on the Wikipedia, for example, we have all of these millions of people going there and basically entering the data and information. That can then be leveraged for understanding new information. So there is crowdsourcing, there is the so-called linked open data. So a lot of databases that have been created by human activities have been put up on the web as an open data, right? And then that can be used for other purposes. For example, geonames. So the names of every location in the world is in this data set, which can then be used to interpret the data. And then data for human, the most important thing. So we can be capturing all kinds of data. Events such as wheezing sound, indoor temperature, humidity, dust, carbon monoxide level, all these relevant to asthma. But what is important is not this data. Most of the time, to the child who is having asthma, or to the parent of the child who is having asthma, or even to the doctors, individual numbers, individual data items are meaningless, are not important, right? If you have, for example, hypertension, then doctor is not paying too much attention to the hypertension every day what you have, your blood pressure. The doctor is paying attention to the sudden rise or significant change from your normal level that you have been able to manage, right? So all this data is not important. What is important is something that you can act upon, such as closing windows at home during day to avoid carbon monoxide in gush so that you could avoid asthma at nights. These are the kind of things that are important. Or I can give you the example from smart energy domain, where you can have data about a lot of different things, energy uses over the day, devices, work, consumption, so many different things. What is important is to be able to basically have this actionable information, the smart data, saying washing and drying has resulted into significant cost, and if you were to change the schedule, you could change significant money. And this also, by the way, needs to be smart. It needs to be human-centric. For example, if this comes with the conclusion that it will save you 3% money in your cost, it's possible that you may not motivate that human to act. Maybe that is not significant enough. What is important is to recognize what is significant for the human, and then perhaps human will act. Say, oh, more than 10% saving in the cost, maybe you can make the human act. So everyone and everything has big data. The example I gave you are the kind of example that you and I can have, right? And if you think about it, this data is being created continuously, all the time. The sensors are measuring it. Your human activities are, capturing all the data. And so that is a big data. It is, in fact, big data is not just about volume, which is an issue with some of these applications, but a lot more about complexity of the data, the variety issue, the velocity issues. This is a very interesting example. Has anybody seen this particular picture and knows the story behind it? The gentleman on the left here is Larry Smart. He is a professor of computer science at UCSD, University of California, San Diego. And he is a quantified self-buff. So what does it mean? He basically likes to use all these devices, all these sensors to measure his body functions and his body activities, everything, all his organ and what he does. And it's a long story, and towards the end of this talk, I have links to his 1 hour long talk, very wonderful talk, that if you have time, I really urge you to watch that. But basically, Larry came with his own conclusion that he has Crohn's disease. Disease with regards to bowel and other things, the bacteria in the gut, and the big imbalance that occurs with the bacteria in the gut that leads to significant challenges and health problem. So Crohn's disease and related disease is what something he came to conclusion himself. Now imagine, now Larry is a smart guy, right? He is a computer scientist, he is not a doctor, and yet he can go to the literature, he can read the literature, and he can interpret the data, right? And from data he could get that actual information saying he has Crohn's disease. He goes to doctors and then works with the doctors to figure out how to manage his disease, right? Now you and I may not be, not all of us can be this smart, and not all of this may be that dedicated, right? So think about developing a solution where each of us have the ability to convert all those data that can be collected about us with the privacy issue addressed into something that is actionable, that tells that helps us manage our health better, right? And that is, if that happens, that means we can give this kind of solutions to somebody in rural India or China and so on and so forth. So for that, I talk about these things. First of all, people live in the physical world while interacting with the cyber and the social worlds, right? We are doing online search. That tells us what we are interested in. Recently, one of my students working with Mayo Clinic did a significant analysis of the kind of search people do when they are interested in cardiovascular disease, or when they are, how much, or major depressive disorder, and so on and so forth. So that tells us something about cyber activities. Our social activities tells us about a number of things. And what if we can leverage all these observations from sensors, knowledges and experience from people to understand, correlate and personalized solutions. So here, a person may have electronic medical record and physical, and health records. You have rich knowledge of the medical domain. You have physiological data from sensors. You have health-related interactions with other humans. You have patients like me and other social media sites where people go and say, oh, I am taking this new medication, but I am having this side effect. Do you also have this side effect? That side effect is not listed in the known side effect for the drug. Then people talk about each other and they learn from that. Very often, adverse drug effect not known or declared by medical pharmaceuticals have been known this way. So all this can be then brought together for making the decisions whereby here person is experiencing heartburn. I will spare you all the details, but ultimately it all leads to an actionable information, actuation, saying contact your doctor. Right? Now don't read these busy slides, and in fact don't read my slides. They are just sort of background information. The thing I want to point here is that how do we then convert these big ideas or these broad ideas and fuzzy ideas into something concrete? I'm a computer scientist, I want to build the things, right? So for that we analyze we created this environment. It consists of these horizontal operators and the vertical operators. Horizontal operators deal with all these variety issues, the heterogeneity of the data and so on and so forth. And for a long time I've been working in this area of semantic web, and that has developed a lot of techniques to be able to deal with heterogeneity. But today I will, because of the limited time, I won't talk much about that. Today I will give you some glimpse of the vertical operator, right? So that vertical operators typically are about converting data into knowledge and something actionable. And so for that we developed this mechanism and we call it IntelliGo. IntelliGo is to perceive. It is based on a Greek word, and the idea here is to, in this particular case, we originally focused on making sense of sensor data, but we already applied that to social data and other data also. So in the case of IntelliGo, we took the ideas, not really techniques, but ideas from cognitive science. And we often in science, we often go to other disciplines and get the ideas. So there have been a number of models for perception, human perception, right? And so we can learn from, what we did is to learn at a conceptual level from cognition models of perception. And one of the things we also learned there is importance of prior knowledge. I'll come to that later. So the perception cycle consists of an abductive part of the cycle, one where data is converted into hypothesis. Low level data is converted into high level abstractions or representation, and a deductive part of the cycle, whereby you could basically say, oh, I have so much information and I have these possibilities and this hypothesis. What additional data could help me reach a better understanding of where I am and to actually validate this hypothesis and things of that nature, right? So that is the deductive part cycle. So there is this cycle that continuously goes on. In fact, that goes on in our brain all the time. That is generally the model, that's the theory. In that what happens here is that you are observing something, I am saying something, and then you say maybe he means this, this, that, and then I say something more in the next few sentences, and what I said makes more sense. In all that context, you are also using your own prior knowledge, your own understanding of the variety of disciplines. Some of you are interpreting what I am saying based on your knowledge of natural language processing. Others are saying, hey, this is relevant to machine learning, and so on and so forth. So we are all using this background knowledge to also improve our understanding. For infrastructure, we use semantic web technologies, and in that context, what happens here is that I think 3 years ago, I initiated and then co-founded a W3C, Worldwide Web Consortium group on semantic sensor networking. So these are slides related to that, and the idea here is that you have a comprehensive model of sensing, and then you represent the facts. For example, elevated blood pressure is a property of hypothyroidism. And with all this bunch of facts related to domain knowledge, you basically create a domain knowledge. In this case, there's a simplistic representation in bipartite graph, but often you need to have probabilistic representation of knowledge. And the same thing can be done for any domain. So I can, again, abstract representation and ontology creation in the case of weather. Now, what we are trying to do here is that in the context of explanation and translation of lower knowledge into higher level, we have to implement this. We try to implement abduction with certain assumptions as deductive processing using OWL-DL. Again, I won't go into this kind of details here. There are papers on each of these things. The links in my talk typically take you to the papers that discuss in detail. And then you have, for example, things behind the scene is that you find, oh, there's palpitation. It can be explained by all those things on the right-hand side. Now, you want to, when you observe something, you may have multiple possible explanations. So you want to say which is the right one, right? That leads to your second part of the cycle, the deductive part of the cycle, right? So for that, then you do discrimination. So here, suppose what these are expected properties for those things, but then you come across, you ask for more information from other sensor, and you say, oh, I find clammy skin. In that case, it is not hypothyroidism, it is hypertension, right? So this kind of stuff, happens in the cycle, and that leads to this converting data into high level abstractions. Hopefully, I painted a general mechanisms. All the details are left for further reading. Now, even that is not sufficient, of course, to build a complete solution. So I am also not I'm very much a practitioner. I like to build the system, and so the thing that I'm talking about, we have a system called K-Health. I'll come to that. We need to convert that all into something that is meaningful for medical decision making. In this case, risk factor, for example. So there is a lot more that goes on. Often people suffer from multiple diseases. There are comorbidity and so on and so forth. So there are things that happen there. I won't go into details of those. So when we try to implement this using OWL-based reasoning, the web ontology language and deductive reasoning, the computation blew up with the so in fact, another important thing was that we wanted to do all this computation on mobile phone. There were reasons for that. For example, there are privacy issues where, because of which I didn't want to take the data of a patient and send it over the cloud and process in the cloud. That includes, that creates certain privacy issues. So I said, the other issue is that I want the solution to be available for any person in the humanity. Remember I mentioned that more than half of the humanity have phone now, and very soon majority will have smartphone. So I want all of them to have the computational capability necessary for them to do this computation. So for that we wanted to do this, what we call intelligence at the edge. So we want to do the computation on the smartphone. Unfortunately, doing so on the smartphone blew up, so the reasoner didn't work well. So we came up with a bit vector based mechanism and operator implementation that then was scalable from tens of nodes to thousands of nodes, and reduce the time from minutes to milliseconds and so on and so forth. So there are some taking. Now I'm going to quickly go through two applications. One, and there are more, but I don't have time to do all of them. In fact, I might have time to do just one of them. So from healthcare, we have applied this general thing I talked about of smart data with PCS data, physical, cyber, social data, to health and particularly ADHF, which is acute decompensated heart failure, asthma in children, and GI patients. And for asthma, for chronic heart disease in GI, the main aspect is that of reducing readmissions. For example, today, so I have video here. I'll again spare the details of that. The internet is not very good here. But the idea is that it costs $17 billion a year because of readmission of chronic heart patients. At a typical hospital, 25% of patients get readmitted within 30 days, 49% within 6 months. Each readmissions on the average costs $50,000, $8,000 to $10,000 a day, 6 days average stay. So this is a kit, that goes for that disease. I'm going to talk about asthma, which affects 300 million people worldwide, right? So here, there is a kit in this case, which consists of sensor drone, and there are many sensors built in that. I think 9 or 12 sensors built into that. And for pulmonary kind of disease, the doctors wanted us to have this node sensor which measures exhaled nitric oxide. But for asthma is a very complex disease. So it's not just related to the what you call physical data alone. Social data and web data, cyber data can also be very important for that. For example, there is information from pollen.com. Many of people are asthmatic, allergic to high degree of pollen. I used to be allergic to ragweed, for example. Air quality outdoor and smog in the cities, that makes people asthmatic, and many things of that nature, right? So these are available as web services. So these are cyber component, right? And people freely talk about tweets. So you have, here you can see real-time health signal from a personal level, meaning for an individual, public level, coming from, let's say, EMR, electronic medical record systems, and population level, pollen level, carbon dioxide, and continuously, these keep on coming in continuously, right? I have passive sensing, sensors around me that can continuously take data every second, every minute. I have active sensing. My mobile phone can ask questions that are relevant to particular, suspected issues with regards to your disease. And I have, all this data coming on the web, continuously being measured, the weather data and so on and so forth. So you have all this data coming, and this is kind of broad level architecture. You have analysis of the data, you have something in there's IntelliGo, there is this more comprehensive system here, and there are computational things, algorithms for risk model. At the end of the day, all you care about is take medication before going to work. Contact the doctor when the risk has gone too high, or there is a onset of asthma, or avoid going out in the evening due to high pollen levels. These are the things that matter to humans. This is what we want to go. This is the smart data. So to be able to do that, I have to infuse the system with the domain-specific knowledge. So in this case, this is the knowledge, the protocol, guideline that doctors use, right? For example, so they have two things here, severity level and the level, how well controlled your asthma is. And here, if you have mild persistent asthma and it is not well controlled, then you will take medium inhaled corticosteroid, right? That will be the protocol that doctor will follow. And the idea here would be that you want to figure out how well controlled the asthma is, and say in some very high level terms. People don't want to get all those, for a normal human who is not a doctor, you don't want all the details. You want something saying, are you doing well? Well, take caution, or no, things are not good. And the other important thing you need, so that was diagnostic, and this prognostic, saying how well controlled is my asthma, and what are the risk factors today? What are the risk factors now? And so you have to say, can I reduce my asthma attacks at night? From that high level thing, you need to understand really many next level of high level abstractions, saying what are the triggers, what are the wheezing level, and so on and so forth, right? Many of these things. So, and then you need to combine all those concepts, those abstractions. You need to evaluate those abstractions in the context of all the data that you have, right? And so these are the data you see, and then these are the observations, these sensors, these are the observations. You have model of the disease here. So there are all these concepts that I showed you in previous slide, and then you have ability to automatically annotate all the data into this machine processable form. This is machine understanding of the data, because the understanding is mapped this way. And so there are well-known, now we have reached a level of science where we can automatically annotate all this data from different sensors in this common way, and on which then we can apply our processing. Use semantic web, this is a sensor model, very comprehensive, I won't go into details of that. And what we do is to convert the data comes from that comes from sensor 150 to a annotated data, systolic blood pressure of that, and represent RDF, to a interpret data saying you have elevated blood pressure, and that can all be represented into the model that I showed you beforehand, can convert that into something that is meaningful for medical decision making, is that hypothyroidism. And that is where that IntelliGo and the kind of smart data processing abstractions come into picture. Okay, so okay. All right. Now let's take another example. Here in this case I am talking about PCS computing for traffic analytics. There are 1 billion or so cars on the road. Just 10% increase, 20% increase in the vehicular traffic rate result into 236% jump in the kind of traffic related challenges. And when the traffic will be, when the number of cars will double in this decade to 2 billion, we have a big problem. We are part of this comprehensive large EU funded project. So we have a number of partners. This is one of the smart city projects that we are doing. So in this case, we have data collected every minute. Just as an example, I'm giving, there's a lot more here, but I'm going to explain things with one example. So we collected data for 3 months for San Francisco area. And that data consists of every minute update of speed, volume, travel time and occupancy, resulting in so many link status observation, so many tweets related to traffic for that area alone, so many active events on the web. So there are websites that will list events. There is a sports game, there is a music game, there is a planned road closure, schedule events, and then these are all unevenly sampled observations collected over 3 minutes. So there is a, you can see it has volume, variety, velocity and veracity problems. And what you are interested here is in that, can we detect onset of traffic congestion? Can we characterize traffic congestion based on events? Can we estimate traffic delays in road network? These are the kind of things, these are actionable things that you are interested in understanding. So you have data of different modalities. These are sensor data, these are tweets, these are data on the web. You have ability to automatically classify the data. So this shows you how we could take the data and basically automatically classify based on all the different departments the city has. So this one relates to, for example, health. Another thing relates to the garbage, and another thing relates to police or something like that, right? So we can tag that. Then you have techniques for understanding some complex issues here. For example, in this tweet, to be able to understand that Half Moon Bay Brewing Company is an entity is a very challenging task. So everybody, anyone here who does text processing would know the challenge in doing that, because Half Moon is also a entity, Half Moon Bay is an entity, a brewing company is an entity, and so on and so forth, right? So to understand these, and so CRF model, conditional random field models, are particularly well suited for these kind of stuff. Other thing you need to do is to kind of then map the data. Internal observations, internal sensor observations need to be mapped to the data out there, external events like active events, schedule events. These need to be mapped together by geography and time as an issue. And then you need to be able to, so here again the linking things going on. You have road data and you have game data, and they all come together, and then they say, oh, it seems like both of them relevant to this particular traffic related slowdown or event. Now what is important and what is interesting and why it makes these things possible, rather complex processing possible, is this use of background knowledge. And so there is this thing about domain experts and knowledge graph, data being coming from, and so here in the concept, here I show concept net 5, there is a lot of knowledge about traffic rules and how one thing affects another thing. You bring that in with regards to the data. So everything comes together, actual data from the road network with the knowledge and understanding of location, causal information, other knowledge, they all come together to help you make decisions. And here I'm showing you a variety of things that happen, data getting interconnected, knowledge being infused. And there is, just the architecture. You have things like point of speech tagging. You have hybrid NER, name entry recognition. You have this OpenStreetMap locations. You have ontology, smart city ontology developed by IBM. You have 511.org human developed taxonomy or hierarchy, and then a whole bunch of algorithms and techniques for processing the data. With all that then leads to, for example, finding information saying that things can be complementary here. So slow traffic from sensor data and accident from textual data come together, right? You have corroborative information. Accident event is supported by information on the web, ground truth. Or you have timely information knowing poor visibility before formal report from the ground truth says that, oh, we have started to see slowdown on the traffic. So there are a whole bunch of examples of these things about accident event and ground events that shows you, corroborative events, it shows you, complementary events here, and so on and so forth. This is an architecture. And, basically, so now I'm wrapping up. I'd like to point to a couple of wonderful talks. I mean, there are many, many things I all the time spend a lot of, I myself spend a lot of time looking at number of videos and other things, as you probably are doing. So now there's so much knowledge on the web. These two are particularly very interesting, where Vinod Khosla talks about the future of healthcare. He mentioned that example of, the information overload on doctors, when instead of 30 biomarkers, when they have 300,000 biomarkers, right? So that's a big challenge that they would be facing. The number of data with all these personalized medicine, with genomics data and so on and so forth coming, this is, significant, right? And so that's a problem. And hopefully I gave you some idea about how we are addressing these things, how we will be able to address even more than that. Larry Smear, he's an example of, this himself identifying Crohn's disease, quantified self. That's something I also talked about today. And he has a wonderful talk on human microbe and the revolution of digital health, right? So some wonderful things there. So let us wrap up, right? Let's see what I talked about today. Big data is everywhere, right? But what is important is that it's not just about serving corporations' need about how to improve their logistics and supply chain and targeting and advertisement. That's where they are using it. But big data is a lot about, in fact, a bigger issue, a bigger interesting aspect of big data is that it affects you and me. And it affects communities. For example, the traffic example I gave you was community example. I did not have time to discuss with you on our work on disaster response. For example, we had collected data and created crisis mapping kind of information for Uttarakhand, North Indian floods and a hurricane there, or cyclone there. We analyzed data for Hurricane Sandy with Oklahoma tornado. For example, FEMA asked us, are there any natural gas-based fires? And we were able to analyze data or the tweets and tell them the last reported fire was 10:30 p.m., right, like that. And many things like that. The data that we processed for Indian floods and cyclone were used by Google Crisis Map. And this was, by the way, we, in the sense, my group and one of my students, Hemant Purohit, coordinated worldwide effort for that. But then it was used by Google Crisis Map in doing the things. So these are all live things. So there have been newspaper articles in some of the biggest media, BBC News and the Atlantic and so on and so forth. That now, hopefully, I get, sort of share with you, and now you'll be thinking about it, saying that data increasingly is growing because we have data about physical world, cyber world, social world. Analysis is not sufficient. To find, analysis will give you a pattern. These are the top 10 patterns. Data science. Data science is wonderful, and that's something that people need now for corporations. But do you think you and I as normal human being interested in our health and well-being are going to do data science? No, we are not. We will need actionable information, contextually relevant personalized information that we can act upon, right? So the next step to data science and kind of things we do today is something I hope I introduced today. I mentioned something bottom up and top down. I didn't get too much time to discuss that in detail, but this is very important that there is a well-known paper, Unreasonable Effectiveness of Big Data, written by a couple of guys I know at Google, very, very well-known scientists. They say, give me all the data and I'll tell you everything that there is to know. No, that's not true. You really need to have that top-down thing. Bottom-up thing by alone is not sufficient. That focus on humans and improve human life and experience is, I think, the holy grail for, at least for me. Yes, making money in a corporation, what they want, that's fine. So I introduced, although I didn't use that word so far today, I call it semantic perception. Right? Perception is very powerful. Think about the data that you consume today just in this talk. The number of bits and bytes of data in all the video that actually hits your eyes and brain, and all the text that you process is in many, many gigabytes. Just the video have been several gigabytes, right? So from that, if I ask you what did I say, you all will be able to explain that in few words. They may be different takeaways for you, but they're all different, right? So, well, that is the thing. So the idea here is to convert all that big data into smart data, something that helps improve our life. I'll end at that. These are my crew, the PhD students, and many of them, their work is represented here. A little bit about our center and Noesis. So let me end.
Thank you very much. Well, as far as his PhD students are concerned, one of them is the 5th highest cited individual in that respective field.
In the web based on 10-year impact.
So we are very proud. Amit used to be a colleague of mine at the University of Georgia for 12.5 years. So I've had first-hand knowledge about the achievements that the students, his former students, have had. Thank you very much. Questions? Yes. Now, if you have any, well, for questions, there's a microphone here, or you can just shout from where you are. If you have questions, please raise your hand. Questions? Please, Dr. Nath. And there is a mic there.
Sir, I enjoy your wonderful lecture. My name is Ashok Nath. I'm from St. Xavier's College, Kolkata. I have 2 simple questions. The first question is, you said that you extract the data from the big data to define something called as a smart data. So my question is, the smart data which you define today, will it remain that smart in the future? Maybe say after 5 years or 10 years, will it remain that smart? Or you have to again redefine your smart data. This is the first question. The second question is this slightly theoretical. You shown in slide number 43, most probably 43, the complexity of asymptotic thing is about of the order N3. So that I want to understand, how do you get this of the order N3?
So the first question was about smart data. Will it? I think you're asking something about will it be smarter in 5 years?
Yes. Yes.
I think I might have done something smart when I defined it smart data, and this is why I would say so. See, I pegged the smart data to something that serves human needs, right? Actionable information for human. I did not define smart data in the context of something arbitrary, something mechanistic, something. And so the point here is that anytime, whether it's today or 5 years or 30 years from now, humans, we hope, we will be there, and we will have needs. Yes, our needs might differ because we have more technology, we have more time for leisure, or we evolve in some ways. But nevertheless, smart data, whatever you want to do, whether we want to improve our entertainment experience, whether we want to improve our health, with regards to that, when we have machinery that converts whatever relevant data that is out there into making better decisions, that will be the smart data. So I think the definition changes by itself all the time. With regards to your question about the use of bit vector based mechanism to convert the very complex data processing technique into linear processing, well, we use the bit vector mechanism. So the idea here was that the logic based mechanism is known to be very high complexity, and that by using the big vectors, you could convert that into sort of matrix kind of operations, and that could become linear. And so we were the smart, I think way of reformulating the problem, and we showed that we can do the same computation we are doing in the deductive reasoning in this bit vector based thing, and it's published in a paper in detail. And so that is the mechanism we use. Now there's a lot more detail there that would require us to go to the board and so on and so forth.
Thank you, sir.
Question?
Yes, there's some.
Please, I'm sorry.
Hi, thank you for this.
May I ask you to just go there, if you would? If you have any questions, there's a microphone here for the benefit of others. Please come to that mic.
Thank you for this insightful presentation. I just have one question. So, if I want to make a system which will extract the smart data from that domain, so you worked in the healthcare, but if I want to work in another domain, the first thing I need is domain ontology. So, being a computer scientist, how can you get that domain expert in that ontology, or how do you build that ontology?
Yeah, so once again, if the questions are clear, in my talk, in the mechanism I showed that prior knowledge. I also showed use of domain ontologies. In the asthma, actually I didn't show the ontology in detail, but there is knowledge. I showed that metrics, for example, and that generally is the start of the ontological knowledge. And the question is, how do you create the knowledge? Ontology creation has been now talked about for a while. In the modern times, it was 1992 report and thesis by Ramnath Guha that brought up that term ontology, conceptualization of the world. And since then, and my group has been both in the academic and the commercial side, we've been very active in developing all kinds of ontologies. We developed well over 50 ontologies. Many of them are public open source ontologies. You can develop them manually, semi-automatically, and automatically. Just as an example, we use electronic medical records. We have some existing knowledge, and then we analyze these sentences, come across fact, and ask whether that is a new fact. And there are certain algorithms to decide whether there is medically relevant facts for this domain, and then ask human expert, is this a new knowledge that you like to add to ontology? And this is just an example of highly semi-automated mechanism for creating highly enriched ontologies. But there is also increasingly the case where there are about more than 300 ontologies at BioPortal, NCBO, National Center for Biomedical Ontology's BioPortal. So in certain domains like biomedicine, large number of ontologies have been developed and are public and you can reuse. And then there are ontologies that can be quickly created from high quality information on things such as link open data or things such as, for example, this concept 5, which had the transportation related knowledge, is out there in public. And it has unidirectional edges. That means the knowledge is not as high quality as we wanted. So we need additional enhancement to put the directionality through certain data analysis. So the point here is basically you can often bootstrap from many different sources and then do some automatic and semi-automatic ways to create the kind of ontology that you do. And today, when I had filed for patent in year 2000, the word ontology was AI-ish and industry would not accept it too much. But now AI is much better accepted, and now there has been all these years of experience in building ontologies of all different kinds in all different domains. So I think we are pretty comfortable in doing ontology as we need.
That will have to be the last question.
Yeah. I'm Dr. Muazzam from NAS, Pakistan. We had actually a project in Germany that was about smart roads and smart cars. We are able to have big data, then to extract smart data, and then to decide even, but still we are unable to deliver the data efficiently to the user, especially if someone is there in the room who has interest about that data, he can receive it.
Your question?
But if someone is moving with, for example, 120 kilometers per hour on the roadside, then is it there any technique to deliver the data efficiently to anyone who is interested throughout the world?
I think so.
Yeah.
I think so.
Because in room you have resources, your means you can efficiently analyze and to take the decision, but to inform other about that decision, you must have an efficient network to deliver your data.
Yeah, but again, remember, I did not so much address the issue of communication, infrastructure, and all that. So if your question is as much as the question about...
The question is that decision is fine to be there, but still to inform the interested people about that.
Let me, good. So question is about, getting the decision or really smart data, meaning to the right person, the analysis that you've done, that is actionable to the right person. So we have to address this issue in a very concrete context of disasters, where people have needs and wants, and people who are willing to supply or can supply resources. When we analyzed 2 million tweets for Oklahoma tornado, only 1.2% of the tweets were asking for some help, needs and wants. Only 0.02% of all the tweets were about some level of qualified level of help. They could help, like for example, somebody who has set up a community center for people to have a temporary stay. The big challenge was connecting the two. That somebody has can give you help 20 miles away, and in that disaster situation you can't go there. That's useless, right? Or if it's not in timely manner, that's also useless. So you have to do spatio-temporal thematic matching of all this data. So indeed, there are, in this case, in activity, there is a paper on first Monday. I'll be happy to give you a pointer to that, whereby we were able to do matches of people needing something and people offering. In fact, interestingly, this work of, that we have done is already part of CrisisNet. Ushahidi, which is the world's most important organization in crisis response and management, has a infrastructure and software called CrisisNet, and this software for matching, giving person, just the right person information, matching them up, is already operationally deployed. But these are examples. So yes, there are techniques that have to be done to really do that matching beyond just identifying that something is relevant, and that's a very important issue. Glad that you brought up the issue.
Well, once again, let's thank Professor Amit Sheth for a very informative talk. And I noticed that there were a few hands up for questions. I'm pretty certain Amit is going to be available after 2 p.m. in the registration area, so you'll be able to kind of offline pose your questions to him. Thank you, Amit. Where are you? Oh, he's gone there. Okay. Well, thank you. Our next, oh, thank you.